In the name of God. Hello, dear students. My name is Masoud. I'm a physics teacher. We are here in Fairkhaw's website to explain physics curriculum. So far, we explained, let's say, 2 sections from chapter 1, and we started, let's say, the 3rd section. We solved some, let's say, some sample problem and practice for you. We discussed a lot of questions about the previous subjects. Right now, let's say this subject is the last subject of this chapter, let's say, and the subject is Newton's law of universal gravitation. Newton's law of universal gravitation is one of the Newton's law of motion. Let's say it talks about the interaction between any two objects, between any two masses. Let's say whether the mass is small or let's say large. So we can apply this law on every two objects in the universe, right? Let's dive in with the lesson. I'm gonna read the definition of this law for you. Newton's law of universal gravitation. This is the statement or definition for this law. It says, Newton says that the gravitational force between any two masses, gravitational force means Fg, F sub g. Gravitational force Fg between any two masses in the universe is directly proportional to number one, to what? To the product of their masses, means m1 multiplied by m2. Simply we can say Fg is directly proportional to m1 multiplied by m2. Or you can say m capital, m small, no problem, it doesn't matter. So this is the first part of the law. The second part of this law, Fg is directly proportional to the inverse square of the distance between their center of their masses. So distance between the center of their masses, we mean r, right? So the second part says that the gravitational force is directly proportional to the inverse of what? Inverse of the square of the distance between the centers of the two objects, right? So Fg, you can read this relationship as Fg is directly proportional to the inverse of the square distance, or you can say a gravitational force is, let's say, inversely proportional to the, let's say, square of distance between the objects. It doesn't matter. In either case, you have to mention inverse, because this law is not let's say, it's an inverse law actually. It's an inverse square law. It's not just an inverse law, and it's not just a square law. It's an inverse square law. Means the distance is inverse and it's squared, right? Keep in mind that gravitational law of, let's say, universal gravitational law of Newton is a, let's say, inverse square law. So let's say the law talks about two things. It talks about the mass of, let's say, interacting objects. Let's say force gravity actually is directly proportional to the product of their masses. That's the first part, and is inversely proportional. Gravitational force is inversely proportional to the square of the distance between the centers of the object, right? So for any two objects, there's this force. We have an example here. There's Earth. It's our globe, and this one is let's say is Moon, right? This is our planet. Our planet has only one moon, and the moon actually I can say, we can say it's a Luna. The name of the moon of Earth is Luna. Actually, you can say moon or Luna, no problem. Moon circles the Earth in an elliptical, let's say, orbit. It circles the Earth in an elliptical, or I can say it orbits the Earth in an elliptical, let's say, path, right? So here, what are these forces? Let me break it down for you. What do we mean by FME? What do we mean by FEM? Does it, let's say, do they differ, or are they, let's say, equal or not? Actually, they are different in nature. They are different in nature, because this one, FEM, means a force of, let's say, Earth on the moon, is the force on moon exerted by Earth. This one, force of Earth, let's say, exerted on the moon. This one, force of moon exerted on Earth. Teacher, what? So, what happens, let's say, in this situation? In this case, I can say, let's say I mentioned it here, FEM is equal to FME in magnitude. They are equal in magnitude. Opposite in direction. What does it mean, opposite in direction? Because the Earth pulls the moon towards itself, like this, and the moon pulls the Earth toward itself as well, right? So they attract one another. There is a mutual interaction between Earth and moon. So, question: why does moon orbit the Earth? Why doesn't Earth orbit the moon? The reason refers to the mass, because Earth is more massive than moon. That's why, let's say, in general, usually the smaller objects actually move the larger objects, right? It doesn't make sense to, let's say, to move the heavier object, let's say, about the lighter object. It doesn't make sense. That's why it's a rule in physics, and in nature it's not. It's a rule of law of nature, right? Uh, this law, let's say, tells us that that for lighter object, let's say, always circle the, let's say, the massive objects, like the moon. Moon orbits the Earth, right? But let me mention this. Actually, moon exerts force on Earth. Moon applies force on Earth, because let's say, there's no, let's say, single force in the universe. Forces in general, let's say, are let's say, are present in pairs. Forces exist in pairs in natures, right? We cannot find a, for example, singular force in the universe. So only there are two forces interact one another based on the Newton's third law, right? Newton's third law, law of, let's say, action and reaction. So, for example, force of moon on Earth, FME, is a force of reaction. No problem. If you name it as action or reaction, it doesn't matter, because these forces are acted, let's say, on the objects simultaneously. So it's optional. If you say FME is action, or FME or if FEM, let's say, it doesn't matter. For example, this one is action and the other one is reaction. Action and reaction are equal in magnitude, opposite in direction, right? They are equal in magnitude, opposite in direction, based on Newton's third law. Let me read this note for you. The gravitational force between Earth and the moon, right? Between Earth and the moon is attractive. So keep in mind that gravity always is attractive, right? It's not repulsive. Gravitational force between any two objects actually does not repel the object. It, let's say, it forces the object to attract one another. It doesn't urge the object to repel one another. It doesn't happen, actually. So this is the nature of the gravity, or gravitational force is attractive. According to Newton's third law, FEM, name this force for me. FEM means force of Earth on Moon, or force exerted on Moon by Earth, is equal to negative. This negative means direction. Negative in physics actually is different from negative in mathematics. Negative in physics means direction, right? It talks about the direction. So it means this one's positive, this one negative, means forces are opposite in direction, but equal in magnitude. They are equal in magnitude. Name this force for me. Force FME means force exerted on Earth by Moon. So they are let's say acting. They are interacting they're interacting each other. They attract one another, and this is about the universal law of gravity. Let's say of Newton, right? Mathematically, I can say Fg is equal to G capital. So this is the constant. Let's say, because whenever we want to, let's say, find a rule for gravitational force, we have to mix these rules, actually, this relationship. The first one, Fg, is directly proportional to m1 multiplied by m2, right? Or m capital, m small, no problem. Either you say m capital, m small, especially in the case of, let's say, dealing with the planets, especially because, for example, one planet is more massive than the other. That's why if you say m capital, m small is nicer. No problem if you use m1, m2 for planets. It's okay, no problem. But let's say both forms are allowed. So this is the first part of the relationship, the first part of the law, m1, m2, or m capital, m small, it doesn't matter. And r capital square or r small square, it doesn't matter. If you use capital letter for r or small letter, no problem, as you like. But here, let's say, whenever you mix, let's say, the relationships together, the first one and the second one, the relationship of mass and relationship, let's say, of distance, whenever you mix them together to find the rule, mathematically a constant appears. This constant actually is called a constant universal of gravitation, right? So let me let's say explain these factors. Fg means gravitational force measured in Newton. This one's gravitational force measured in G capital, constant of universal gravitation, and it's measured in what? Look here. And this is the question of national exam. Actually, I include this question in next lesson. Let's say I'll show it to you. But right now, I want to let's say I want you to focus on it in advance before we let's encounter this question. I want you to derive the unit of the G from this equation. Teacher, how do you derive the unit of let's say G capital? I mean, G capital is a new, let's say, constant for us. Is a constant of universal gravitation. All right. Let me let's say drive it for you. I want you to rearrange this equation for G capital. I can say G capital is equal to cross multiply the equation. Whenever you cross multiply the equation, m capital, m small, or m1, m2 goes down because, right? Let me write m1, m2. m1, m2 goes down because G is multiplied by m1, m2. So guys, let's keep going. I'm gonna let's say drive this rule for G exactly. I told you m capital, m small, or m1, m2 goes down, and the other variables go, let's say, go up. Fg r squared, right? So in this situation, I want you to, let's say, determine the unit of G for me. One by one, I want you to tell me the unit. Fg is measured in Newton. R is measured in meter. and it's square, so it will be Newton meter square divided by m1, m2. M1 is mass of the object 1 multiplied by mass of the object 2. So kilogram multiplied by kilogram becomes kilogram square. So Newton meter square over kilogram square, right? This is the unit of G. And G is a constant. I want you to memorize it. Let's say, and the value of G is 6.67 multiplied by 10 to the power negative 11 Newton meter square over kilogram square. M1 and M2, you know, are measured, let's say, in kilogram, and they are masses of two objects. And R stands for the distance between the objects' centers, measured in meters. Actual distance is measured in, let's say, in meters in SI. All right. Let me tell you about the gravitational force. Let's say, in general, what's the definition of gravitational force? I want you to distinguish between gravitational force and the law of gravitational force, right? The law of, let's say, universal law of gravitational force is different from the gravitational force itself. Gravitational force, let's say, focuses on the force, let's say, on one object, right? But if you say law of, let's say, universal law of gravity or universal law of gravitational force, in this case, you have to mention two things. You have to mention the distance. You have to mention the, let's say, relationship, whether it's directly or inversely. But here, it doesn't need to go through the subject. It's not, let's say, it doesn't need to say the detail about the subject. Simply, you can say gravitational force is a mutual force of attraction between particles of matter. That's it. Mutual force of attraction between the parts of a matter, right? So features of gravitational force. I summarize some features or properties for you for gravitational force. Let's discuss it together. Maybe you know some of them. Let's say you got this information in previous years, maybe in grade 11 or maybe in secondary, let's say, stage. Let's say you got this information. Let me read them for you. What are the features of gravitational force? The first one is attractive. I told you gravitational force never be repulsive. It's attractive forever, right? It's attractive. Number two, gravitational force exists between two masses. It exists actually between two masses. Whether I told you the mass is microscopic, let's say like particles, like subatomic particles, or the masses are, let's say, are huge, like the planets or the stars. So force of gravity or gravitational force exists between any two masses, regardless of the mass of the objects. Number three, gravitational force is independent of the medium between the objects. It's independent, let's say, of the medium. What does it mean? Whether there's a medium between two objects, for example, and Newton said that even between two chairs in a room, there's a gravitational force, right? And and the medium between these chairs, actually, there's a medium. The medium is air, matter. So the matter, whether the matter exists, whether the medium exists between two objects, or let's say it doesn't exist, maybe between the planets, for example, between the planet Earth and its moon, actually, right? There's no any object, right? There's no any medium. There's a space, and gravitational force, let's say, appears between these objects. Think about the gravitational force between the sun and the planets, right? even there is no, let's say, medium between the sun and the planets, but gravitational force actually does its action, right? Let's say it takes its action, it does its work. Gravitational force, let's say, forces the, let's say, forces the sun and forces the, let's say, planets to attract one another. That's why, regardless of the medium, right, irrespective of the medium, gravitational force exists between any two objects in the universe. That's about the third one. And the last one, gravitational force is independent of size and composition of matter. Yeah, it's clear. Whether the object is microscopic, like proton and neutron, let's say electron, there's an attraction between these particles within the atom, right? And let's say whether the object is, let's say, huge, like planets and stars, let's say gravitational forces existed between them. And the last one, composition of matter. And it's clear, you know, that the stars consist of hot gases. Stars composed of plasma, right? And you know that the planet, the composition of planet is solid. Actually, I'm talking about the, for example, terrestrial planet, especially about the fourth, let's say, beginning the planets. They are made of rock. So whether the object is, let's say, rocky, or the object is gaseous, or even the object is liquid, no problem. It doesn't matter. Gravitational force existed between the objects. Thank you guys for watching this video. I hope you enjoyed this lecture, and bye bye.